Welcome to the lecture series on CFD, Part 1. This is Lecture 1 on approaches to solving flow problems. In this lecture, I'll present to you briefly the basic concepts of fluid flow and the main approaches to its analysis. I will then explain pros and cons of experimental analysis and numerical simulations as the main approaches to flow analysis. Two important questions will be then answered from my point of view. What do you need to know to be successful with CFD, and what is CFD nowadays used for? Finally, I'll briefly introduce to you one state-of-the-art CFD software which I mostly use, and then close with a brief summary. We call fluid any substance which offers no resistance to external shear forces. Even the smallest shear force will cause the deformation of a fluid element. We distinguish between liquids and gases, but both kinds of fluid obey the same laws of motion, and in most practical cases of interest, we can consider them as a continuum. The forces which drive fluid flow can be classified as surface and body forces. Examples of surface forces are pressure, normal to surface, and shear, tangential to surface, while gravity and rotational forces are prominent examples of body forces. Fluids differ by their macroscopic properties, which significantly affect the motion. The most important properties are density and viscosity, but others, like surface tension, specific heat, or Prandtl number, may significantly affect the flow under certain conditions. Fluid properties may often be considered constant, but in many cases they depend on temperature, pressure, and possibly other physical properties. Fluid flows can be classified in many ways, but most often this is done according to the flow regime, compressibility effects, and type of fluid. Flows at very low speed are called creeping flows. This happens often in porous media and micro devices. As the flow speed is increased, fluid inertia becomes important, but as long as fluid particles follow smooth trajectories, the flow is called laminar. Laminar flows can be both steady and unsteady. A further increase in speed leads to instabilities which make the flow turbulent. The process of transition from laminar to turbulent state of the flow is an important topic on its own. If compressibility effects are not important, we call the flow incompressible, otherwise it is compressible. Compressible flows can be subsonic, transonic, supersonic, or hypersonic according to Mach number. Note that both liquids and gases can be considered as incompressible or compressible, depending on Mach number and whether acoustic effects are of importance. In the latter case, even a low-speed flow may need to be treated as compressible. Most fluids of practical importance are considered to be Newtonian type, that is, obeying Newtonian law of viscosity. Flows of non-Newtonian fluids are important in some applications, and CFD methods we shall deal with here can be applied to some but not all of them. Many other phenomena associated with fluid flow, like heat transfer, buoyancy effects, multi-phase interaction, or phase change. Some of such effects will be covered in this course, but some are too special and will not be included. The Navier-Stokes equations are an accurate mathematical model for most laminar and turbulent flows. However, these equations cannot be solved analytically, except for a handful of trivial flows in situations where most terms in equations drop out because of various assumptions considered valid for given conditions. Examples are laminar fully developed flows in pipes and channels. Under some conditions, approximate analytical solutions can be obtained, like for lubrication flows in bearings. In those cases, the assumptions which make the equation solvable are not strictly fulfilled, but the ignorance errors are considered small. Dimensional analysis and empirical information is sometimes used to create diagrams, tables, or formulas which are useful for early design applications. However, the lack of generality due to a limited range of parameters imposes its limitations to this approach. Experiments are still widely used to perform testing of products prior to their release to the market, but numerical simulations are gradually replacing experiments in many situations. These two approaches will therefore be discussed in more detail in the following slides. In an experiment, a real flow is measured, but it may not be the one that we are interested in. In most experiments, the objects are scaled down and there is a significant uncertainty in extrapolation from laboratory to the full scale. A complete similarity is seldom possible. For example, to match the Reynolds number, the flow around a smaller aircraft must be faster, but then the Mach number increases and we may move from a subsonic to a supersonic flow regime, which becomes non-comparable. The same is true for floating objects like ships, where the Reynolds and the Froude number cannot be kept the same in model and in full scale. In addition, real conditions on boundaries or the lack thereof cannot be reproduced in a laboratory. Many quantities of interest often either cannot be measured at all or not with a sufficient accuracy. While it is usually easy to measure the integral quantities like forces and moments, flow details are often difficult to measure. Accurate velocity measurements, for example with laser Doppler velocimetry, can only be done pointwise, which takes time and requires ensuring that the flow does not change in the meantime, that is, keeping the temperature and boundary conditions the same all the time. Building the models, instrumenting them, and running the experiment is time-consuming and costly. Experiments are suitable to determine the is state in a flow for a given geometry and boundary conditions, but they are not suitable for parametric studies and design optimization. The measurement for one condition does not give a clue what will happen if one or more parameters are changed. Numerical simulations have many advantages over experiments, but also one significant source of uncertainty. CFD can be done at real scale, no need for using scaled-down or scaled-up models, thus there are no scale effects. In a CFD simulation, realistic boundary conditions can usually be accounted for, like relative motion between a car and the road. There is no need to limit the size of the flow domain like in a wind tunnel. Also, one can account for all geometry details, like appendages on a ship or detailed geometry of a car. One of the most important advantages of CFD is that it delivers all the relevant information about the flow: velocity, pressure, temperature, forces, heat fluxes, and so on, in space and time. This often gives the engineers ideas and clues why the results are different than expected if things go wrong. Experiments are limited by the availability of the laboratory facilities. Another experiment cannot be started in one facility before the running one is finished. CFD offers the possibility to speed up the analysis by running simulations in parallel, possibly in a cloud. If money is available, one can hire more people to intensify the analysis. In a simulation, one can compute any derived quantity, including those that cannot be measured at all. Simulations can be automated to perform parametric studies, what-if scenarios, etc. They can be conducted in an early design stage before anything is built. In addition, CFD can be coupled with optimization software tools to scan the design space and find the optimum design much faster than would be possible otherwise. The only downside of CFD simulations is that the solutions are not exact. They always contain errors from several sources, and these errors must be analyzed to assess the reliability of the solutions. The problem is that this task is often difficult and cannot be conducted with certainty. Otherwise, it would have been too easy. Because it is not so easy to ensure that the results from CFD simulations are reliable, engineers doing flow simulations should possess certain know-how to be successful. 10 people solving the same problem using the same CFD software will produce different results after a different period of time. Successful are those who deliver more accurate solutions faster. You should have a solid knowledge of theoretical fluid dynamics and flow features like boundary layers, shear layers, flow separation, vortex generation, shedding, etc. The more you know about the flow to be simulated, the better you can adapt the grid design and other simulation parameters to the expected flow features and obtain a good solution without many trials. In addition, you should have a solid knowledge of computational methods embedded in the CFD tool that you are using, especially those related to available physics models, boundary conditions, optimization of grid quality, error estimation, etc. This enables you to select the most appropriate simulation setup and deliver a solution with a sufficient accuracy within a short period of time. In times of user-friendly software and artificial intelligence, knowledge is the only competitive advantage that you can have. Many beginners may ask themselves, what is CFD nowadays used for? What might become its role in future? Here are some examples from my perspective. CFD is frequently used to solve problems when something goes wrong, often when all else fails. Flow visualization, detection of flow unsteadiness, vortex shedding, zones of flow cooling, and so on, help engineers to detect the cause of the problem. Knowing the cause usually leads to ideas for problem solution. Simulation can also confirm whether the ideas work or not. CFD helps to understand the physics of the flow. It is especially important if one wants to improve the design, introduce the measures to avoid possible problems, for example heat shielding to prevent overheating of critical components, measures to suppress possible unsteadiness or vortex shedding, etc. A very important role of CFD is to help design experiments. It is always advisable to perform flow simulation prior to setting up an experiment. This helps to identify critical flow zones, the range of velocity, pressure or temperature variation, etc. In this way, one can select the most appropriate instruments and sensors, design measurement locations and strategy, data processing, and so on. CFD is an invaluable tool for flow analysis in an early design stage or to evaluate the ideas of innovative designs for which no past experience exists. Knowledge acquired before any prototype is built is a competitive advantage. Changing designs in later stages becomes very expensive as this may require many system changes. CFD allows an analysis of interaction of various system components. It is not enough to design an optimal hull, propeller or rudder alone, assuming ideal flat water surface. They have to work in an optimal manner together under realistic wind and wave conditions. It is often more valuable to perform a system analysis and capture component interactions with a coarser grid and lower accuracy than to conduct a very accurate component analysis but missing the interaction effects. CFD is especially useful in the analysis of heat management, cooling, heating, heat protection, etc. It is also used to simulate processes in product manufacturing like coating, drying, welding, casting, etc. Many multi-phase and multi-physics problems can also be simulated with a sufficient accuracy for practical applications like flows with free surfaces, cavitation, flow-induced motion of flying or floating bodies, flow-induced deformation of solid bodies, electrochemical like in batteries, or electromagnetic like in electromotors, effects, and so on. The early days of CFD use in engineering were not easy. Jokes were made about colorful fluid dynamics or colors for directors. Grid generation was very tedious and took weeks. Physics modeling capabilities were very limited, as well as the post-processing capabilities. The breakthrough came with the proof that the results were useful and could help solve problems where other approaches failed. Here is an example of the analysis of coolant flow in the 4-cylinder block of an internal combustion engine. Some zones were not cooled well enough and cracks were developing. Finding out why by doing experiment was not very promising. A rather coarse grid with about 60,000 cells identified correctly the critical zones and the suggested modification of coolant channels for which simulation indicated improvements has proven to solve the problem. This analysis was performed almost 40 years ago using the StarCD software. Over the past 40 years, giant steps were made in CFD software development. The modern state-of-the-art software, for example SimSet and StarCCM Plus from Siemens, has an intuitive graphical user interface and allows an easy automation of many types of analysis. A CAD tool is available which allows the creation, import and repair of complex car models, as can be seen from this car model here. Unstructured, locally refined surface and volume grids, including those made of arbitrary polyhedral control volumes, are generated automatically, allowing for a high-fidelity representation of the flow domain. Prism layers are created along walls for boundary layer resolution and within thin solid structures for optimal heat transfer analysis. Parallel computing, including the use of GPUs, is employed to enable efficient computations with grids containing hundreds of millions of control volumes. Extensive reporting, monitoring, and post-processing capabilities are available to allow engineers to extract quantities of interest for visual and detailed inspection and assessment. Here is an example of visualization of flow around a car. We see a smooth flow in front and above the car, but a very turbulent flow around the front wheel and in the wake. This video shows simulation of a maneuvering of a high-speed boat in waves. The diagrams on the left show the variation of heave, pitch and roll motion on the boat. Here we see the applied power, the rudder motion and position held, and the vessel speed. In this corner we see the boat's orientation with respect to wave propagation direction. Such simulations were until recently only possible using invested flow models, but those are not sufficiently accurate because they do not account for viscosity, turbulence, and breaking wave effects. In this simulation, Reynolds average Navier-Stokes equations are solved and the free surface can break, eject droplets, and trap air pockets. Cavitation on propeller and rudder can also be simulated. Finally, this animation shows visualization of a complex flow in a turbomachine. Let me now briefly show to you how a modern CFD software, here SimCenter StarCCM Plus, works. It is based on client-server architecture. The server is doing computation, usually in a workstation, cluster, or somewhere in the cloud, while the client is used as an interface between the user and the server for data input and visualization of reports, monitors, and scenes. Multiple clients can be connected from different parts of the world via internet to the same server, thus allowing collaborative analysis of results while the simulation is still in progress. This is often done to control the progress of long-lasting simulations and check whether any of the parameters need to be adjusted. When a client is started, this window appears. You can choose to create a new simulation, to open an existing one, or to connect to a running server. In this case, I am opening in serial mode an existing simulation which I can find by browsing from my directories. In this node, I can edit the CAD model, here a model of a lead-driven cavity flow. The flow domain was obtained by first creating two sketches, one for the rolls with belt and the other for the lower and upper cavity. The sketches are extruded to create solid models. The belt assembly is then subtracted from cavities to create the volume body of fluid. Boundary surfaces are given names. The next step is to create automatic meshing operations. We need three models: surface remesher, trim cell mesher, and prism layer mesher. Their properties can be adjusted as needed. Meshing control takes place using default and custom parameters. The most important parameter is the base size. All other geometric parameters can be related to the base size so that grid refinement can be performed by just reducing the base size and pushing the grid generation button. Prism layers usually need to be adjusted, notably the number of layers, the layer thickness, and the stretching parameters. Custom control can be related to edges, surfaces, and volumes. Predefined paths are used to specify the cell size and other parameters within these control entities. The next step is to define physics models governing the fluid flow. Present flow is steady and laminar, a coupled solution model is used, and fluid properties are selected to obtain the desired Reynolds number. The CAD path describing the flow domain has been earlier assigned to flow region. Here we see all named solution domain boundaries at which we can specify the appropriate boundary conditions. If we open the geometry scene, we can see the location of each boundary as it is highlighted in the scene when we click on it. Under Automation Field Functions, the user can create various functions that can be used to specify simulation parameters or extract derived quantities. For each simulation, one has to specify stopping criteria for the iterative solution process. Here one can define reports, for example, the force on the bottom wall and on the lid above the cavity. One can create monitors and plots from these forces so that one can follow how these quantities are changing during the iteration process or in a simulation of an unsteady flow. For example, in the plot from a bottom wall force monitor, we see how the force converged to one value on the coarse grid and how much it changed when the grid was refined 3 times. The changes are each time becoming smaller and the convergence appears to be of second order. Here we see the profile of vertical velocity along the horizontal center line on the current grid. Many kinds of plots can be defined prior to performing the simulation. When the computation is finished, the results are immediately ready and they can be also viewed while simulation is in progress. There is no need for a classical post-processing if one knows in advance what one wants to see. Another kind of visualization are scenes, which can show contours, vectors, streamlines, etc. Here is an example of pressure visualization. It varies significantly on the gaps and near them. This plot shows velocity vectors. We are only interested in the flow within the lower cavity. thus we do not need a fine grid in the upper cavity. Instead of vectors, one can show flow patterns using line convolution integrals shown here. We see here how the moving belt creates several recirculation zones in both lower and upper cavity. The grid is locally refined to resolve all important flow features. This is especially needed when small gaps or other important features need to be resolved while sparing cells where they are not needed. Here we can check all solution domain representations, while under tools many additional features can be defined, like annotations, coordinate systems, motion of various parts, reference frames, tables, etc. Everything we define, all generated grids, solution data, reports, monitors, scenes, etc. is saved in a single file, which is actually a database. This makes it easy for someone else to later repeat the simulation, with or without modifications. Backward compatibility is guaranteed. I have recently opened a simulation file created 12 years ago and it ran without problems. However, the results were not exactly the same because the discretization methods have slightly changed during these 12 years. Let me briefly summarize the main takeaways from this lesson. CFD is an important tool for design and optimization of both external and internal flows. For a CFD practitioner, it is important to have a solid knowledge of both fluid dynamics and CFD methods. Fluid flow is a nonlinear phenomenon and simple extrapolation often does not work. Here is an example of flow around a sphere. When the sphere is moved, the drag drops suddenly around the Reynolds number 300,000 from about 0.5 to 0.06 before starting to gradually increase again as the Reynolds number increases. If the sphere is rough, the drag crisis takes place earlier. The drag doesn't drop so much, but it recovers to a higher value than when the sphere is moved. This animation here shows the large eddy simulation of flow around a smooth sphere at the Reynolds number of 100,000. The flow is laminar upstream and around the sphere and its wake. It separates laminarly, but the shear layer becomes unstable, the Kelvin-Helmholtz instability, and turns turbulent, making the whole wake of the sphere turbulent. The flow is very complex with a lot of intermittency and wake wobbling. As the Reynolds number increases to the critical Reynolds number, the turbulent shear layer after laminar separation starts interacting with the wall, like in this case where the Reynolds number is 300,000. This postpones the wake separation and reduces the recirculation zone. This is why the drag reduces and the large eddy simulation is able to predict this complex flow variation as a function of the Reynolds number.